Greetings and welcome to a new video about digital controller implementation. This is our example number 3. In this example we will look at the Cascade implementation of a digital controller. We will see that we can split up a transfer function, which is in this case a second order, in two first order configurations as shown here. And this Cascade implementation has the following advantage: it is less sensitive to coefficient problems or coefficient sensitivity problems. And then we can also use that advantage when you split this second order system, for example in this case, to a first order system, two first orders in Cascade. So we'll see how we do that and also see the steps in this example. So let's look at our problem. We have the following transfer function of a digital controller given. That's shown here. So it is again DZ, which is our digital controller or digital computer, which is from ETU. And this are again for clarification, there's a sample and hold and are planned together. And this is the transfer function of the controller itself. So you see there's a second order system. We also have a gain here of 5. So what we want is a flowchart for the implementation of this digital controller. And we will need to use a first order transfer functions, 2 of them, in Cascade to implement this. You can of course do this also directly as we have discussed in example number 2. But we'll do that now in a different way with 2 first order systems transfer functions in Cascade. So let's see how that works out. The solutions: first we factorize our transfer function. We have this. The factorization means actually that you use factors for the numerator and denominator. So we can say this is then z plus 2 times z plus 3 for the numerator. And for this we have z plus 0.2 and z plus 0.5. Then you will have this situation. Now, moving on, we can now say the following step: change the exponents. That means the following: we need to convert the z's here into z to the power minus 1. So we need to see the delay expressions. So we divide the numerator and the denominator by the z to the power, or actually z to z, and also again by z. So we actually divide by z squared. So since we have 2 fractions or 2 factorizations. Then we have the following. So you divide by z here, for example, let's start with that one. You divide by z, that means you have 1 here, and then also 2 times z to the power minus 1. It also counts for this one, so you see that. So everything with a z will be a 1, and everything with a number will get a z to the power minus 1. We do another one, so you divide again the numerator and denominator by z. We have this expression. You see again the z is 1, and the other one gets a z to the power minus 1. And also for the denominator. So we have now our expression as required. Now we will split this in product. So split the product. We have now actually a product of 3 terms. We have a 5. This. We have a fraction here, which is 1 plus 2 z to the power minus 1 over 1 plus 0.2 z to the power minus 1. And also the other one. Now we have 3 parts. This is the gain stage. The second one is the first order transfer function stage. Another one is again a first order transfer function, but it's done in the second stage. So we can say the general first order transfer function was discussed in example number 1 is given by this expression. We see the 3 parameters, a0, a1 and b1. Now we will need to use this in this stage and also in this stage. So for the first and the second stage. So for the first stage and for the second stage, we can also designate that more exactly, more carefully by saying, okay, for the first stage we use the prime, and for the second stage we use now the double prime. So this is actually what I did. So we have exact same transfer function, but different coefficients, of course. Now we will now need to look at the transfer function of the first stage, transfer function of the second stage, and then compare that with our general first order transfer function. Now looking at the first stage, I see it is 1 plus 2z to the power minus 1. That means actually a0 and a1 both are prime, are 1 and 2, and then b1 prime will be then 0.2. That's shown here. In a similar form, you look at this one and you also determine the a0, a1 and b1, and then of course double primes. So you get the 1, 3, 0.5. That's all shown here. So this is actually the necessary information we need to develop our flowcharts. So now the flowchart for the first transfer function, which is our first order transfer function, stage 1, and the gain together. So we can now take them together. This part here is just the gain. So without this, you can say this is just a wire, so we have only a gain of 1 here, but now this complete structure we know from example number 1 is the flowchart for a first order transfer function. And this is the A0 prime, here A1 prime, and here the B1 prime. Now we need to also have the gain, which is then this, the K here, so I just designate it as K. Now we need to now convert this to the actual flowchart with the numbers required. Now the gain is 5, so that means this will be a 5, this will be a 1 as said here, this is 2, and this is 0. It is all shown here, and this is the gain again. Now we have our first stage, including the gain. So this and the first order transfer function. Now moving on to the second stage, now the first order transfer function again. Now looking at the stage 2. Again the same configuration, but now we don't have this gain here. And remember, it was ended with the X star here. So if I go back, it's better actually to see that. So this was actually from the E error to the X, which is actually an intermediate signal. And that X will be then connected to the input of the second stage, which is the second first order transfer function. That's actually important to see here. So if I go on, and that will then start at X. So you can see it start at X and then it ends at U. Now we again have here the A0, A1 and B1, all of them of course double primes. And now we need to convert that to the required flowchart with the numbers, and now you see 1, 3 and 0.5. Now we have everything. Now we need to make the complete transfer function by connecting them together. That means we have this. You see, this is the gain stage, this is the first order, the first stage, this is the first order, but the second stage. You see the intermediate signal here again, that's the X star. So we're going from the error all the way to U, that is our transfer function required. Now we have it, and this is our flowchart really required for this system. Alright guys, this is our example number 3 for this digital controller implementation using 2 first order transfer functions in Cascade. So we implement this, and again this is handy when you want less sensitivity for coefficient changes or coefficient parameters in your design. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. The next example we will discuss a third order system where we also use the Cascade implementation. So see you next time in another video. Take care.